All right, well, we're not falling for 1. That's good, but we're still not quite there yet. Which wire is which? Okay, wire 1 is the smaller thickness, right? So we have I1 is equal to NAUE1, and I2 is equal to N4A, right? 4 times that area, UE2, which is the same E, so I'll just say E1. And so we have 4 times NAUE1. So I2 is 4 times I1, but I1 is 1/4, right? I1 is 1/4 of I2. So be careful which one they're asking for. But you have the key idea here is this is the thinner wire. The electric fields are the same, right? And it turns out, in this particular case, the drift speeds are the same. The mobility is a material property. It's the same nichrome alloy in both, right? So the mobility is the same. So the electrons are moving the same speed in both of these circuits, but in the second circuit, you just have a thicker wire. So because it's proportional to the area, you just have more electrons per second because they're moving at the same speed, but you just have a fatter pipe, essentially, right? Fatter wire. So you can get more electrons per second moving past than in circuit number 1. Okay. Questions here? This shouldn't probably have caused as much trouble as maybe it did. So yeah, yes. Okay. So the question is, does the loop rule take priority? You got to be careful about the node rule. The node rule is talking about I in and I out within a single circuit. There's no rule that says I can relate the current in this circuit to a current in a different circuit. Okay, so I can't say current here is equal to current here. It's two different situations, right? What is the node rule telling us? Well, this is a very simple circuit. We have the same thickness of wire throughout. So all it's telling me is that anywhere in this wire, because the current everywhere is the same, so if I pick any piece of this as a node, I in is equal to I out, which means NAUE in is equal to NAUE out. All this is telling me is that I got to have the same electric field throughout that wire. Okay, and similarly, I can apply the node rule to this circuit and say I got to have the same electric field throughout that wire. But then what I do is I apply the loop rule to 2 different circuits and find, oh look, those electric fields in this particular case turn out to be the same because it's the same length. Okay. Someone else had a question. Yes. That's a good question. N is the number of electrons per cubic meter. So if you knew, let's see, you could work out so we know from various material properties and measurements that metals give up a certain number of electrons to the mobile electron C. Okay, and I think most transition metals typically give up 1 electron to the electron C that's free to float about. Okay, so if you knew, for example, the density of the metal, okay, so the metal has a certain number of grams per cubic meter, and you knew the molar mass, right, the number of grams per mole, you could figure out essentially the number density of atoms, the number of atoms there are in a cubic meter of a particular material. And then you can say, okay, if each atom is then giving up 1 electron, I've got N, right? So really it's just depending on sort of the density of the material. How many atoms are there per cubic meter in this material? If they each give up 1 electron, then that's the number of electrons per cubic meter. So it really just depends on sort of the physical properties, density, molar mass of that particular metal. Okay. The mobility, what does it depend on? it essentially is a measurement of how easily can electrons move through a particular metal. Okay, if given a certain electric field, how fast are they going to move? And so essentially you're measuring how often do they collide with the lattice, right? We have this sort of simple model of the sort of a ball and spring model of a solid where we have these atoms bound by spring-like forces, and then electrons are coming through, and occasionally they collide with one of the atoms that make up the lattice of the structure, and then they give their energy to the lattice, right? And so we have this sort of start-stop motion, and we average that out to see how fast the electrons are moving. What things could affect the mobility? Well, for example, the temperature. Okay, if in sort of a very simplistic picture, if you imagine these atoms are vibrating with a higher amplitude, then there's going to be and that essentially is what temperature is at the microscopic level, right? The sort of thermal energy is a measurement of how much the atoms are vibrating around. Well, then you can kind of see that if they're vibrating with a larger amplitude, there's going to be a greater chance for one of these electrons to actually hit and lose its kinetic energy and slow down. Essentially, the resistance, we'll talk about resistance in the next class, the resistance goes up because it gets hotter, okay? And so therefore the mobility goes down. So mobility is really another one of these physical property measurements, but it depends on temperature. The hotter something is, the less easily the electrons can travel through. Yes, so in principle, iron may have a different number of atoms. Iron's denser than copper, for example. So iron may have a larger number of atoms per cubic meter than copper does. Now, I'm not sure of that. In fact, most atoms. Let me rephrase that. Okay, the number of atoms per cubic meter is something that comes really from the quantum mechanical properties, the size of the atom, right? And that's something we can sort of reason out from these things, which we can look at up on from a periodic table. So those are purely material properties. N and U are purely material properties. Okay, and it doesn't matter how much of substance you have because it's on a N is on a per cubic meter basis, right? So it's independent of how much you have, and the mobility is sort of on a per electron basis in some sense. So it doesn't matter how much you have; it's just purely a material property.